Hi there, welcome back to this video. This is 4-2 and this is the second lesson on linear motion. Today we're going to go ahead and talk about some linear motion problems. Alright, so diving back into our notes here is example number 3. And example number 3 they say is calculator active. So you will need your calculator for this example. And they tell us for 0 to 2, a bug is moving along an x-axis with v of t defined as t squared times sine of t cubed minus 1.5 t. Okay, well, if you have a calculator active problem, you're going to want to go ahead and quickly define that function in your calculator. They're going to ask you to do lots of things, especially if this is an FRQ response problem. So I went ahead and I defined that function, and then let's go ahead and read part A. It says find a of 0.7, and is the bug speeding up or slowing down at t equals 0.7. So we're going to take this first part, a of 0.7. Okay, well, a of 0.7, that's the same thing as v prime of 0.7. So what we're going to go ahead and do is we're going to calculate that in our calculator. So menu, calculus, derivative at a point. The value is 0.7. And then the function, I've already defined this as v of x. So v of x. Okay, be careful. Again, I know they define it as t in the problem, so if you use t's in your calculator, be consistent with whatever your independent variable is. Okay, and so we get the acceleration at 0.7 is 0.921 or 920 if you truncate. Okay, so I found the acceleration by taking the derivative of a velocity. There it is. Ta-da! Okay, well, how do I know if the bug is speeding up or slowing down? Well, remember back to the first video, an object is speeding up or slowing down if the sign values are exactly the same for acceleration and velocity. Now, I know acceleration is negative, but what's velocity at 0.7? Well, what I can go ahead and do is I can just go ahead and take my function. I defined it, and I'm just going to say, okay, what is velocity at 0.7? And there is the value. V of 0.7 is equal to negative 0.318. Okay, well, both of those values are negative. So that means that the bug is speeding up. Its velocity is going in a negative direction, and its acceleration is negative. Therefore, the bug is speeding up. Okay, so since v of 0.7 and a of 0. Actually, I'll say this. Since v of 0.7 is less than 0 and a of 0.7 is less than 0, the bug is speeding up. Okay. Awesome. All right, next, B. Find any values of t in the interval 1 to 2 when the bug is at rest. When the bug is at rest. Okay, so what does it mean when they say the bug is at rest? Well, that means that the velocity is equal to 0. So I'm looking for when the velocity is equal to 0 on the interval 1 to 2. So what I'm going to go ahead and do is I'm just going to graph this function. So I'm going to go control doc, and I'm going to add a graph. And I've already defined it, so right here I can hit the variable v of x, and whoa, there is our graph. Okay, so what I'm going to go ahead and do is I want to zoom in right in this region. So I'm going to go menu, window, box. I really only care, let's even say to here. That's about to 2.45. Okay. So, and then what I want to do is I want to adjust my window. Let's go ahead and, actually, we'll do it this way. We'll go 0 to 4, and we'll make our x scale by 1. I want to go by 1s. We'll go by 0.5s. 0.5. Okay. letting me enter? Okay, there we go. All right, so here's our graph, and you can go ahead and see, that here's 1, so 1 to 2 would be here. Where is this object at rest? Where is it at rest? So it looks like the velocity is 0 here and here. So I want to go ahead and I want to go to Analyze Graph, and I want to find zeros. So I want to find what this 0 is. Okay, at 1.225, and then another 0, which is here at 1.801. Okay, so I'm going to say t equals 1.225 and t equals 1.801. Okay, there you go. So that's when the bug is at rest. The bug is at rest there. All right, C, find the open intervals on 0 to 2 when the particle is moving to the right. Okay, when a particle is moving to the right, when velocity is positive, moving right, when v of t is greater than 0. Okay, so on 0 to 2, where is it moving to the right? So I'm going to go back to my graph, and I'm just going to look at this. So 0 to 2, again, that ends here. Well, when velocity is positive, so isn't velocity positive from here to here? Okay, it's above the x-axis. So that interval is going to be 1.225, 1.801, because that's when velocity is positive. That's when velocity is positive. There we go. D, find the acceleration of the bug when velocity is equal to -1. Find the acceleration, so that's a of some value, when v of t equals -1. Okay, so what I need to do is I need to take v of t and I need to set that equal to -1. So I'm going to go to my graph again, and I want to find out, okay, where is it equal to -1? So how am I going to do this? Well, I'm going to go ahead and I'm going to graph a second function. So one thing you can do is you can hit tab and it will bring up a second function, and I'm just going to define it as -1. Okay, so here I have v of t is equal to -1. V of t is equal to -1. Okay, and I got to find what this intersection is right here. So menu, analyze graph, intersection. So right here. And that looks like 1.837. 1.837. Okay, and I'm going to go ahead and write that down, jot that number down. So t is equal to 1.837. Actually, I'm going to take like 5 decimals because I want to be precise. 1.83687. And now another thing that you can do when you have calculators, say I want to use this value and I want to be that quantity and I want it to be exact. I can go ahead and I can store this value. So Control VAR, and I want it to store. It's not letting me do this. I'm going to hit OK. There we go. Okay, so I'm going to click on it. It should highlight it like this. And I'm going to hit Control VAR, so this will store it. And you'll notice it says VAR, what's the variable? What do you want to title it? And I'm going to call it just A. I'm going to call it point A. You'll notice it bolds it. So now it's stored that exact value. Okay, well, what I want to do is I want to find what is the acceleration here. So that's where velocity is equal to -1. So I want the acceleration at this value. Acceleration at 1.83687. And I'm using so many decimals because I want to be precise. I don't want to have a rounding error. So using that variable is so much better because it will store all of it and give you a precise answer. So what I'm going to do now is I'm going to go back to my calculator, and I want to take the derivative of velocity. Something you can do is I'm just going to go up till it highlights this, because isn't this the derivative of velocity? And I can hit enter, and it just copies it down, which is really awesome. And then I don't want the x value to be 0.7, I want it to be a. Whatever that value of a was that we stored, or if you're using like 5 decimal places, you can use 1.83687. So I go ahead and enter that, and we get negative 28.874. Okay, and there you have it. That is your value. And I also want to define this. This is v prime of 1.83687. Okay, so there you go. If you're working on the AP test and you define a variable, it's important that you write that down, that you store that number. If you're going to use that variable, just so the reader knows. Like if you wrote here, you know, v prime of a, which is equal to a of a, which gives us negative 28, you need to store that value. So you would just say a to 1.83687, or the other way around actually. So this to a, so that the reader knows that whenever you use a, that's what you're talking about. Okay, that is example number 3, calculator active. All right, moving on. Example 4. Example 4 is a fresh look at linear motion, but given information in a table. So they say for 0 less than or equal to t less than or equal to 8 seconds, a particle p moves along an x-axis. The position, velocity, and acceleration of particle p are differentiable and modeled by the functions x sub p, v sub p, and a sub p respectively. So they're just saying here's the position, here's the velocity, and here's the acceleration. Selected values for position, velocity, and acceleration based upon time are shown in the table above, where xp of t, x sub p of t, is measured in meters. Okay, I'm glad they mentioned the units. So this is in meters. Well, velocity is going to be meters based upon time, and we're talking about seconds. So just talking about units, this is going to be meters per second. And then acceleration, that's meters per second squared. Okay, and units can often help you when you're trying to dissect problems. So A, is particle P moving towards or away from the origin at time t equals 4? Is it moving towards or away from the origin? Well, in order to figure this out, I need to know what's the position at time 4. I need to know where is the particle. So the particle at time 4 is equal to 6. And I'll just think about this on a number line. Here's the origin. Here's the particle. It's at 6. Okay? Well, now that I have its position, what is its velocity? What's the velocity at 4? And if I read that, that tells me it's -1. So that tells me that this particle is moving left. It's moving left. So is it moving towards the origin? Yes, moving away. Or it's moving towards the origin, not away. So we can say, since x sub p of 4 is equal to 6, the particle is left of the origin, or is right of the origin. And v sub p of 4 is equal to -1. So the particle is moving left towards the origin. Okay, and there's our response. It was at 6, it's moving left. Awesome. Okay, next one, B. Is particle P speeding up or slowing down at time t equals 7? Well, we kind of already talked about this in the last example. I need to know what is the velocity at 7 and then what is the acceleration at 7. And if those signs are the same, it's speeding up. If it's slowing down, or sorry, if they're opposite, then it's slowing down. So let's look at velocity and acceleration, and both of those are negative. We have -4 and -3. We can say, since v sub p of 7 is less than 0 and a sub p of 7 is less than 0, the particle is speeding up at t equals 7. There we go. Awesome. Very, very straightforward. Okay, C. Use the data in the table to approximate v sub p of 2. Now, I'm not given information about 2. I want v sub p of 2, and they want us to approximate velocity. Well, in order to approximate, we're going to use position. I'm going to take the average change of position relative to 2. So I'm going to use these timetables, 1 and 3, and this is like a problem that we just did in the last lesson where I'm given a table of values, but now you really have to discern which set of values I'm going to do. So if I want velocity, well, that's the change in position. So I'm going to take the average change in position in order to estimate velocity, okay? So I'm going to go ahead and calculate this. So we get this is, sorry, x sub p of 3 minus x sub p of 1. That's what I'm doing, which gives us 8 minus 2, which is 6 over 2, which is equal to 3. And our units are going to be in meters per second. Okay, all right. D. Is there a time C where 1 is less than C less than 7 such that v sub p of t is equal to 0? Justify your answer. Well, they're asking you if a certain value exists. So you need an existence theorem. And the only one that we've talked about thus far is the intermediate value theorem. So we need to go ahead and we need to answer some conditions. Condition number 1, is v, the function that they're asking about, is it continuous? Well, they say in the stem that it is differentiable. V sub p of t is differentiable. So v sub p of t is continuous. If it's differentiable, it is continuous. Okay, next, what I need to do is I need to see if this value, if this k value is between the function values at v of 1 and at v of 7. So I'm going to use my table. I'm going to go ahead and we're going to look at this. So v of 1, it looks like that's 5. And v of 7, that is -4. Okay, and lo and behold, 0 is between those values. So I have my two conditions satisfied. We can go ahead and we can write a conclusion now. So we say, since v sub p of t is continuous and 0 is between v of 1 and v of 7. And then here, so I stated my conditions. Now I'm just going to go ahead and copy exactly what they said. There is a time C where C is between 1 and 7. 1 is less than C, which is less than 7. Such that v sub p of t is equal to 0. Okay? Awesome. That is the intermediate value theorem. Okay. Last question, E. And this one's a fun one. They say for 5 less than or equal to t less than or equal to 8, a second particle q moves along the same axis. The position of the particle q is modeled by x sub q of t, which is equal to 12 minus t minus 10 quantity squared. At t equals 7, are particles q, p, and q moving toward or away from each other? Explain your reasoning. Now, what really helps here is a picture or an image. And so I have an axis here, and I'm going to go ahead and I'm going to put the origin on this number line. What I need to know is what's the position? Like where even is particle p at 7? So x sub p of 7, if I am using my data table at 7, it's at 5. This is equal to 5. So the position of p is 5. So here is p. Here's p. Okay? And then I also need to know what is the position of q at 7. So I'm just going to use the function that they gave us here. So 12 minus 7 minus 10 squared. So 12 minus 9, which is 3. So this one's at 3. So here's q. Okay. And are those particles moving towards each other? Well, I don't know. I just know their position. I know they're at 3 and at 5. But what will tell me which direction they're going is their velocity. So I'm going to analyze the velocity of p at 7. And if I look at the velocity, that is -4. So what that tells me is it tells me that p is moving left. So I know that that particle is moving towards q. But is q moving towards p? Are they moving towards each other? So then I'm going to go ahead and I'm going to say, okay, what is q sub p of 7? Well, in order to know what v sub q is, I have to go ahead and take a derivative. So I need the derivative of position. So the derivative of position, here's position. The derivative of that is going to give me the velocity of q. So that would be -2 times t minus 10. There's the velocity. Okay, and I'm going to calculate now at 7. So -2 times positive 7, -7, 7 minus 10, which gives us -2 times -3, which is 6. Okay, so that means right. It's moving right. Okay, so q is moving right. And ta-da! There we go. It is moving right. Okay, so we can go ahead and say, particles p and q are moving toward each other because x sub p of 7 is equal to 5, and x sub q of 7 is equal to 3. And v of p of 7 is equal to -4, which means p is moving left. And v of q of 7 is equal to 6, which means q is moving right. Okay, and there's our justification. All right, so There have been lots of different types of position, velocity, and acceleration questions over the course of these two videos. Hopefully that you can take away what it means if an object is standing still. Its velocity is 0. Hopefully you can tell me when an object is moving right. Well, that's if its velocity is greater than 0. You can tell me if a velocity is moving left, if its velocity is negative. How do I find the acceleration? Take the derivative of velocity. How do we find velocity given position? You take a derivative. Those are the key ideas that you need to take away from this lesson, and we'll continue doing more practice with this. Please give me a thumbs up, like this video, subscribe for more awesome math videos. Catch you in the next one. Peace.